Before I continued with the next problems, I just wanted to review something about the definition of the second law. So the definition of the second law is telling us that the total entropy of an isolated system cannot decrease over time, all right, and remains constant if all processes are reversible. So if I look at the first question that we solved, we saw that the change in entropy was positive. It was a value greater than 1, greater than 0. What does that mean? What that means, essentially, is that the process is spontaneous. So it's not reversible, right? Because the entropy would have to be 0. Yes, the entropy would have to be 0 for the process to be able to go in both directions, right? But the entropy is greater than 0. What that means is that this process spontaneously goes in one direction. So this process, when I remove the divider, the gas will spontaneously readjust and move around to accommodate that pressure. However, the gas will never spontaneously move all the way, all in one half of the tank, creating 400 kPa pressure on one side and a vacuum on the other. That just won't naturally, according to the laws of thermodynamics, occur. And if you think about it, that does also make sense, right? You would expect diffusion to equalize, right? This is what we've learned and what we've learned in previous courses as well, Brownian motion, things like that. So, having said that, I'm going to come to 8.7, which is my nozzle question. So the question states that air initially at 800 kPa and 100 degrees C with a velocity of 25 meters per second is expanded in an adiabatic nozzle with a polytropic process with N equal to 1.3. It exits the nozzle with a pressure of 180 kPa. Determine the temperature and velocity at the nozzle exit. So let's just organize my knowns and unknowns. I know that I have a P1 of 800 kPa. I know that I have a T1 equal to 100 degrees C, which is 373 Kelvin. And I know that I have an initial velocity of 25 meters per second. I know that the process here has N equal, N is equal to 1.3, and that at the outlet I have a pressure 180. I have a CP value. Okay, so the solution said 1.3. However, if you look at the question says 1.3 and the solution I think also used 1.3. I solved it using 1.4. I think I misread the question, but I solved it using 1.4 because that's the K value I got out of the table. So I jumped too quickly to the table there. So the numerical solution, my numerical final answer will be slightly different from the solution, but the process is exactly the same. So I solved it with K equal to 1.4. So I'll just change it here. And with a CP of 1.005. So we're told that it is isentropic. We're told that it's adiabatic and polytropic. So knowing that it is polytropic, that will allow me to use some of the equations that we have saved up. So I'm going to start by using the first law, right? If I look at the first law equation for the flow, because here we have a flow in and a flow out. So I know there's no change in total internal energy. It's adiabatic, so there's no heat. There's no work done either. There's no compression, expansion, anything like that. Nothing fancy's happening. There is a flow rate though. And I know I have a flow in minus my flow out. And then I also have a velocity in. And then I will have a velocity out. Now, what can I do with this? I am going to I am going to start by isolating V2, because that's part of what I'm asked to solve for. So if I isolate for V2 squared, I just divided by 2000 immediately to convert my joules into kilojoules. That's where that 2000 is coming from. It's my unit conversion. So I'm going to see that I have 2000 H1 minus H2 plus V1 squared. And because I don't know the enthalpies, I am going to rewrite this in terms of temperature, right? So then I get Cp T1 minus T2 plus V1 squared. However, I don't know the temperatures either. I don't know my T2 actually, my T2. So at this point, my V2 is unknown. And my T2 is unknown, which is a little bit unfortunate. So what I'm going to start by doing is I'm going to have to jump to my polytropic process in order to be able to solve for that. So what I'm going to work with is T2 over T1 is equal to P2 over P1, then minus 1 over N. So I know that my T2 is going to be T1 divided by P2 over P1. 373 Kelvin, and my pressures are 180 kPa, and then my other pressure was 800. And yes, no, I did it. I solved with 1.4. I got the value off the table there. 243.56 Kelvin. And if I substitute my temperature in, I'm going to see that V2 is going to be 2000. My CP was 1.005 kilojoules per kilogram Kelvin. And then my temperature difference was 373 Kelvin minus 243.56 Kelvin. And then plus my velocity term, which, will give me 25 squared, and I'm going to need to take the, all right, and then you're going to need to take the root of that. Oh, okay, I can't. Boy. And this will give me a velocity of 510.1 meters per second. Okay, sorry about that. I paused the recording to double check my arithmetic, and the answer should be 510.7 meters per second. So this question in reality is not all that different from what we were doing with the first law. The only notion here which was important is that isentropic relationships are polytropic as well.